Okay. Let's get started. Chemistry of acid and hydrides. I think that's where we left off at. This is a symmetrical anhydride. We've mentioned these before. Each side is the same. The R groups of the carbonyls are the same. Okay. This is a mixed anhydride, like a benzene ring on one side and a methyl on the other. We do need to know the anhydride functional group, oxygen bonded to 2 carbonyls. This one is acetic anhydride because it comes from this acid, which is acetic acid. And as we've mentioned before, this is the acyl group. Or acetyl group. Acyl is more of a generic. This could be anything. If it's a methyl carbonyl, it's acetyl. Both of those begin with AC, but this is your AC group. Okay? So acetic acid can be abbreviated the acetyl OH, but this is acetic anhydride because it's an oxygen and there's 2 acyl groups on each side, or acetyl groups. And so this is a common abbreviation of acetic anhydride, and it is mentioned in the 8-week lab as you can make the acetamide from your aminofluorine. Okay? Synthesis of anhydrides. We've already seen one synthesis. Number 1, you can refer back to that. All right? Because we used an acid chloride to make the anhydride. All right? We've already covered that. A new method is number 2. And this will tell us where the name anhydride comes from. If you take a carboxylic acid, such as acetic acid, and just heat the bejeebies out of it, okay, high temperature, it will self-react. 2 equivalents will self-react, and you will get the anhydride plus water. Okay? So you're removing water. And if this is done, greater than 100 degrees Celsius, how will the water exist? As steam. And so it will come out as a gas and it'll be driven away. And if you remove water, that's anhydrous. And the product you get out of this is called an anhydride. Okay? Basically, you got 2 molecules. I'll draw the other one this way. Basically, this oxygen attacks carbonyl, and you lose water. And so it's a self-condensation reaction. I'm not going to look at the mechanism for that. There's only one mechanism for this test. It's NAS, nucleophilic acyl substitution. Okay? We're attacking carbonyls. Okay? When you attack carbonyl, electrons go up because you break the pi bond first. From there, it's all just sort of downhill, and you do what you need to do. You got to take care of the proton. Okay? At what point do you take care of the proton? All right? So you can look there and see that reaction. But, so 2 equivalents of this gives 1 equivalent of this. Okay? So in terms of stoichiometry, you got 2. Okay. This only works for symmetrical anhydrides. You just take acetic acid and heat it up, okay, you can get that product. If you take 2 different acids, you're going to get a mess. Because what can happen? You got both of these in the flask. This could react with itself. That would give this symmetrical anhydride. This could react with itself. That would give acetic anhydride. Or the 2 different acids could react, and that would give the mixed anhydride. You're going to get 3 possible products, and they're going to be very hard to separate and purify. So the thermal dehydration, that is, this heating to dehydrate it, only works when you want to make a symmetrical anhydride from 1 starting acid. Right? You don't want to make a mess like that. Hard to purify. Cyclic anhydrides, these are actually very common. If you take a diacid and heat the bejeebies out of it, you can dehydrate it, and one acid will react with the other. Basically, one oxygen will bond to the carbonyl and you will use water. Okay, you got to see this, and you'll get a cyclic anhydride. Right? Oxygen bonded to two carbonyls in the ring. That's succinic acid. This is called succinic anhydride. Diacid. Did we do Diels-Alder in organic 1? What did we use? We used a diene. We generated a diene from butadiene sulfone. What did we react it with? Maleic anhydride. Remember that? Look back. Maleic anhydride. Okay. Maleic anhydride, don't draw here, it just has a double bond loop. And then that will react with the diene. 4 plus 2 is what? 6. Okay. You look back at that lab. When I introduced that lab, I said, this is an anhydride. We'll see it in organic 2. Well, now it's organic 2. Okay. And we talked a little bit about the chemistry there. Okay. So you look back at that Diels-Alder lab. Because if you put a double bond here, that's called maleic acid. Okay, so those are very common. We'll actually use them when we look at reacting anhydrides. Okay. And now we're ready to look at that. Anhydride, this being acetic anhydride. You attack one carbonyl, the other oxygen carbonyl is all going to be the leaving group. So that's analogous to maybe an acid chloride, okay? With the chlorine as your leaving group. You don't attack both. You attack one, the other is leaving. So nucleophile can come in here and attack electrons up, eventually back down, kick off the leaving group. And we can get an acyl substitution. And the leaving group was this thing here, right? All right? That's common chemistry. Now, you got to note that half of the anhydride is lost as the leaving group. So it's actually poor atom economy. And this is particularly important if the acid portion is expensive. This is also why acid chlorides are better than anhydrides. Okay, suppose you had a carboxylic acid and you wanted to do some chemistry here. Well, first we need to convert it to something else. What's the problem with having the H here? Look at the very top of the page. What was the problem? I'm sorry, it was on the top of the previous page. Having the acidic H. Okay? Well, we can convert this to the acid chloride, no longer has the acidic H. Very good for acyl substitution. Attack, kick off the chlorine. Okay? 1 mole of this gives 1 mole of that. Okay? But you could also do this with the anhydride. But guess what? 1 mole of this only gives a half a mole of the anhydride. Because it's a 1 to 2 ratio. I'm sorry, the other way. It's a 2 to 1 ratio. You need 2 of these to make an anhydride. So you need twice the amount of this to make the anhydride. So if you got 1 mole of this, you're only going to get a half a mole of this. Okay? Now we can come in, if we want to make an amide, we can react this with ammonia or something as the example. Okay? And we can come in and we can displace the chlorine by a nucleophilic acyl substitution mechanism, and we can make an amide. If you got 1 mole of this, you're going to get 1 mole of that. But down here, well, the same thing. If ammonia comes in, electrons up, eventually back down and kick that off, you'll get an amide. But if you got a half a mole of this, you're going to get a half a mole of amide. And the remainder will be a half a mole of the leaving group. So basically, if you got 1 mole of this, you get 1 mole of amide. But if you got 1 mole here, and you go this route, you're only going to get a half a mole of amide. Okay? Because the other half of this just became leaving group, and you're going to put this in the waste container? Well, that's not good if this is expensive. Or if you spent a year trying to make this. You want to put half of it in the waste container? No. You'd rather put chlorine in the waste container. What's the byproduct up here? Ammonium chloride. Not ammonium acetate or whatever. Okay? So, anhydrides can be used as acylating reagents, but you have poor atom economy. That's okay if the anhydride is cheap, such as acetic anhydride, very cheap. But for bigger molecules, you typically want to go with the acid chloride, better atom economy. Yes?
For the reaction C up there, does that work for non-symmetrical anhydrides too?
Yes. When the anhydride is non-symmetrical, you have to determine which carbonyl you're going to detect. When it's symmetrical, they're the same. We will look at that on the next page. Okay. Although we have problem with atom economy, nonetheless, we can use anhydrides as acylating reagents. What do you get for product here? Anybody? Okay, first one we'll get that acetamide, right? Next one, methylamine, right? Product here. Get that product there, we'll have amide and a carboxylic acid. And the one below, we'll get what functional group there? Ester. Yeah? Okay, mixed anhydrides, as was mentioned. Let's look at them. Some acid chlorides are not stable. This acid chloride is not stable. Instead, this anhydride is stable and we can use it as an acylating reagent. Now that's not a mixed anhydride, but I'm just telling you that some acid chlorides are not stable and anhydrides are. Over here, this acid chloride is not stable, just with an H here. But this mixed anhydride is stable, and we can make it. How would you make it? This could be made from formic acid. React formic acid with some type of base, such as triethylamine. Come back with an acyl group with a leaving group, such as a chlorine. And this would give this mixed anhydride. At that point, this mixed anhydride, we can react with some type of nucleophile, as shown here. And here we have nucleophile, and we can attack one of the carbonyls. Which carbonyl would we attack? Which carbonyl is most electrophilic? They're not the same.
The second carbonate?
Which one?
The second one?
Why the second?
Because it has two electronegative atoms below the electron density towards them. It has two oxygen connected to the second carbonyl rather than the first one. Oh, no, right.
They both have
They
two
both have
oxygens connected to them.
The difference is one has an H and one has a methyl. Which one are we going to attack? Do what? Sterics could be a factor, yeah. And so you're suggesting the one on the left, okay. What about electronic factors? Methyl versus H. What does a methyl do electronically?
Donates and nothing.
Donates? Yes. Yes. The methyl donates. So what's that going to do to electrophilic character of this carbonyl carbon?
Decrease it.
Do it?
Decrease the electron.
Decrease it, yes. So these electrons attack here, electrons up. Okay. Is it okay if I do it, just come back down and kick this off? Can't do that on a quiz or test. Okay? All right? Good? And we're going to get a product that looks like this here. We can get the amide. And that reagent is pretty selective. I've done this chemistry, I've made this reagent, and it will react selectively here as opposed to here. And you will get a product where you have an H here, okay? And plus what? Why triethylamine? If we did not use triethylamine, what are we going to get here? We get acetic acid, right? Okay. Acetic acid may be acidic enough to protonate the amylin. So why use triethylamine? To take the H. And so we would have this plus triethylamine, and we would end like that. Next one. This is not really an anhydride because it's an oxygen bonded to this carbonyl, but it's analogous to an anhydride, and it would be mixed. That is, the two carbonyls are different. Which carbonyl would we attack here? Well, we know methyl donates. What is this oxygen going to do? It's also going to donate. Donate how? Donate how?
Everybody hear her? Didn't hear?
By group one, the resonance.
Okay, group one, you're referring to EAS? Okay, we're obviously not doing EAS, but I understand what you're saying. You need to sort of be more clear about that. Oxygen donating by resonance, which is a stronger effect? The oxygen donating by resonance or the methyl donating by induction?
Oxygen.
Yes. Yes. Yeah, the resonance donation is going to be larger. So which carbon is more electrophilic? Over here. And what's going to react with that carbonyl? Which lone pair is most nucleophilic? What's the nucleophile? Nitrogen, right? So we attack here, electrons up, back down, kick off the oxygen. Okay? Do I need to do this full mechanism? Electrons up to give oxygen minus. That's intermediate. And the electrons back down. We don't have a proton here. Until, when do we have a proton that we got to take care of? When did we take care of it up there? After this attack, didn't we have something like that maybe? And this could take the H, and that's how we would have had the H here before I erased it. But instead of that taking the H, what took the H? Triethylamine. Yes. Well, same thing down here. Something's going to take an H from this. Well, triethylamine. You can work through your mechanism, but the product here would be oxygen here, nitrogen, now bonded to carbonyl, and the carbonyl has what on it? A methyl. Plus what? What else would we get here? We're going to get CO2 plus ethanol. Everybody good? Everybody good? What type of functional group did we make? Amide. Specifically, what type of amide? Carbonyl methyl. What type of amide did we make? Acetamide, right? Everybody good? Biological application. Anhydrides of phosphoric acid. This is phosphoric acid. If you heat the bejeebies out of it, it will eliminate water and you'll get an anhydride. This will be an anhydride between, this will bond to another phosphoric acid. Analogous to a carboxylic acid bonding to another. And you'll get what's called pyrophosphoric acid. Oxygen bonded to two carbonyls. Well, here oxygen bonded to two of these phosphorus type things. Analogous to a carbonyl. Pyro means heat. And so this was heated. So it goes by kind of a different name, but the pyro means that it was heated. That's how it was formed. Pyrophosphoric acid is seen in biochemistry. Okay. Now you still have these acidic H's. And so under basic conditions, these H's can actually all be removed. And it can exist like this. And that's called pyrophosphate. And you will see this in biochemistry. But pyrophosphoric acid is analogous to a carboxylic acid anhydride. Okay. I wonder why nobody asked about this here. Everybody good on CO2, all this over here?
What happened to the triangle?
What do you mean, what happened to it?
Like causing the reaction before we had the triangle algae.
Uh-huh.
What happened to it in this reaction? Do you get the same thing?
I would ask you to work through it and see how you get these two and see what the fate of the triethylamine would be. Okay, chemistry of esters. We've already seen synthesis of esters back with 2B and 3B. Synthesis of heroin from morphine. Okay. You know, a long time ago, morphine has been known for 500 years. And back in the 1800s, it was found if you take morphine and heat it with acetic anhydride, we get a new compound. And that compound has even more potent properties for killing pain and narcotic properties. Okay? So you can hydrate, yeah? And the compound you get upon heating morphine with acetic anhydride is today called heroin. Okay? Heroin is well, it's an illegal substance, but it's often used as a recreational drug. And on page 47 in your lab manual workbook, we see heroin. There's morphine over there. You got two OH groups. But in heroin, each OH group is now what? What type of functional group? Ester. Okay? All right. Acetyl. Isn't that an acetyl group? Isn't that an acetyl group? Okay. Heroin is also called diacetylmorphine or diacetyl. You can also say acetyl. Okay. Which is more polar, morphine or heroin? Which is more polar, morphine or heroin? Right? Why morphine? What do you mean, like donators?
Like electron donators.
I don't understand electron donators. What do you mean electron donators? Sounds like you're either looking to do an AES reaction on a ring or you're looking to do a redox reaction when you say electron donators. Can you clarify? Can you clarify anyway? Okay. Anybody else? Which one's more polar? Okay. That's heroin, and what's the compound at the top? Codeine. What's the difference? Codeine is where one of the oxygens has a methyl added to it. Okay. We've seen that before. I think I had that problem as maybe a Williamson ether synthesis. Okay. So there's an example of making an ester. But we really have already seen making esters because we're really cycling around. When we look at acid chlorides, well, we can make esters from acid chlorides, or maybe we can make esters from acids, carboxylic acids, like using a Fischer esterification. So we've already kind of looked at that. So there's really nothing here new to look at under esters. But what we will look at is reactivity of esters. And a common reaction of esters is hydrolysis back to the carboxylic acid. Okay? Now this requires more than just pure water. Because if you remember our reactivity scale, acid chlorides and anhydrides will react with pure water, but esters and amides will not. Okay? Because of that, esters and amides will be found in nature, but acid chlorides and anhydrides will not. Okay? Hydrolysis back to carboxylic acid. As we showed on our diagram, all acid derivatives can be hydrolyzed back to the acid, right? All right? Using either aqueous acid or aqueous base. This is just a reverse of a Fischer esterification. And when we covered Fischer esterification, I said, okay, can we reverse this? And we did. We went from product and we reversed it all the way back to starting material. Okay? So it's just a reverse. So you should know that reaction already. Products here. How do we do here? I have product here. Products. Anybody have something you'd like me to look at? The one on the next page shows hydrolysis under basic conditions. Here we can use sodium hydroxide followed by H plus workup, and we can get carboxylic acid, methanol. Why do we need the H plus workup here? Under basic conditions, we're making an acid. The acid's going to exist in the basic form. We need to put the proton on with the workup, right? Provide product down here. It's going to be what? Alcohol plus the acetic acid? Saponification of a triglyceride to a soap. This is a triglyceride. It comes from glycerol. Glycerol is a trialcohol. Looks a little funny, but it's actually 3 carbons. Each carbon has an OH group. Glycerol. Okay? If you make esters on each of these oxygen, it's called a triglyceride. And it's a common fat in your body. 2 common triglycerides, also fatty acids. But actually, that portion would come from a fatty acid. If you hydrolyze a triglyceride, what would you get? Well, you would get glycerol, right? Plus what? Plus the fatty acid. But how many equivalents of this would you get? 3 equivalents? Okay? This would be in the basic form, unless you did an H plus workup. But what is this here typically? What are these fatty acid anions used as? Soap. Okay? And so we can make soap from fat, like animal fat. Okay? And saponification sort of means soap forming. When you hydrolyze an ester under basic conditions, it's often called saponification. Just a general term.
Would you do that for other reasons than to make soap? I'm just curious. Like if that's what it, like, is that the only thing you would ever
Well, the reaction above, we saponified that ester above.
Okay.
Because anytime you hydrolyze an ester with basic conditions, it can be called a saponification.
Okay.
Okay, hydrolysis of a lactone. What is a lactone? A cyclic ester. This is a cyclic ester. You see that? The ester. But the oxygen and the carbonyl are in a ring. Okay? Lactone. A lactone can be hydrolyzed with hydroxide followed by H plus workup. What would you get here? We would get H plus workup. We get this carboxylic acid, but we have an OH here on the end, yeah? What is this down here? Vitamin C? Vitamin C is a lactone, yeah? Ignore the alkene, ignore the OH groups. What do we have here? It's a ring, but what's in the ring? Carbonyl, oxygen. Okay? So vitamin C is an example of a lactone.
So will that bust open
It could.
and then,
It could be hydrolyzed open. They can do other chemistry. Vitamin C is largely known as an antioxidant because this alkene here is very reactive towards electrophiles, including oxygen or oxygenated species. So the chemistry right here is sort of the major chemistry of vitamin C. You don't often see it opened up because the body is not highly basic conditions,
right,
but it could theoretically be. You're going to be able to get strongly more basic conditions in the chemistry lab with like sodium hydroxide. That's sort of a double enol that I circled. It's very electron rich, alkene. It'll react with. You can do redox chemistry there. Thioesters. Thioesters. Right here on the end. Okay? If that was an oxygen, what would that be on the end here? An ester. But instead we have a sulfur bonding to carbonyl, a thioester. And what is the name of this big molecule, which you will see in biochemistry? Acetyl-CoA enzyme or coenzyme. Yeah? Where's the acetyl group? Oh, right here. Okay, it's the acetyl group. Can you convert an ester to another acid derivative? Yes, you can go downhill to the amide. React this ester with something like methylamine. We can get the methylamide plus ethanol, yeah? Now this can be done. It's probably going to require some heat. Esters are not that electrophilic. Acid chlorides or hydrides are much more electrophilic. Okay? the best way to make this amide would be, instead of the ester, to use like the acid chloride. I mean, that's going to be much more reactive. That doesn't mean you cannot do it with an ester. You can. This would be the more common way to propose to do it. Acid chlorides and anhydrides are more reactive intermediates. And of course, between those two, acid chloride is better because acid anhydrides suffer from what? Atom economy, unless the anhydride is cheap. Okay, chemistry of amides, aka carboxylides, aka amides. We've already seen synthesis. Synthesis from acid chlorides, anhydrides, or even esters, such as we just seen there. So we've already seen synthesis of amides. Okay? Amides. You cannot convert them to any other acid derivative. You can only convert them back to the carboxylic acid. At least I'm talking directly. Of course, once you get to the carboxylic acid, then you can convert it to anything you want. Okay? But you can hydrolyze an amide back to the carboxylic acid. And the nitrogen would be released as ammonia, but if you're under acidic conditions, ammonia will exist as ammonia. Down here, hydrolyzing with base, hydroxide, right? And we can hydrolyze this acetamide to the amine plus acetate. And the products will be in the basic form because we're under basic conditions. Down here we have a cyclic amide. Cyclic amides are called lactams. Okay? You can hydrolyze open the lactam. Just because it's cyclic doesn't mean you cannot hydrolyze it. Okay? That's caprolactam, and the product there, once opened up, is that product is then used to make nylon. Lactams is drugs. Penicillins. If you look right here, we have a 4-membered ring lactam. So lactams are seen occasionally as drugs, and penicillin is very important. And in that case, yes, the lactam is often opened up. And so in terms of drug metabolism, hydrolysis and opening of the lactam is a common metabolic route. And that destroys the drug. If you want the drug to last longer, you would not want that to happen. And actually, there are some penicillins that are clavulanic acid is given, and clavulanic acid inhibits the enzyme that promotes hydrolysis of this lactam. And that is a combination drug. You ever heard of augmentin? Augmentin has clavulanic acid added to it to inhibit the hydrolysis of the lactam. And so the penicillin has been augmented with an additive, and it's called augmentin. Acidity of amides, imides, okay? Let's look at the acidity here. This is just an amine, going to have a pK of about 30. If we put one carbonyl on, it's now an amide. Amides have a pK of about 18 to 20 for this hydrogen. If you put 2 carbonyls on, this H now has a pK of about 10 to 12. Well, what is this called? It's actually analogous to an anhydride. If it was oxygen under my hand, it would be an anhydride, yeah? With nitrogen on 2 carbonyls, it's called an imide. And the imide H is fairly acidic. Acidic enough that we can deprotonate it with base, with aqueous base, hydroxide. And this leads us to the Gabriel synthesis of primary amines. If you start with phthalimid, which is the imide of phthalic acid, because that's benzoic acid, but if you have another carboxyl group, ortho, that's called phthalic acid. And if you can close this and make an imide, it's called phthalimid. Phthalimid. It's analogous to the anhydride. If you made an anhydride here, what would it look like? It would look like that, right? That's called phthalic anhydride. Phthalic acid, phthalic anhydride, this is called phthalimid. Because it's an imide, okay? But if you take phthalimid and treat it with hydroxide, you can remove the H, right? Hydroxide takes the H. Now this is ionic, right? This is minus, and this is plus, right? Just like KCl, that's plus, and this is minus, right? Okay, that's plus and minus. But this nitrogen anion, let's forget about the spectator ion. The nitrogen anion can be reactive in an SN2. And so we can have maybe something with a leaving group, and this can attack and do an SN2, and we can alkylate the phthalimid nitrogen. Pretty standard chemistry. We could have did that in organic 1. Now, the nitrogen carbonyl bonds can be hydrolyzed. It's like a double amide, kind of. And if you do a double hydrolysis, you're going to liberate the nitrogen as the primary amine. Already redrawn that, but you'll generate phthalic acid again.
Why do you have to put the R group on it first?
You do not. What we're showing here is a Gabriel synthesis of primary amines. This is a way to make primary amines. Gabriel synthesis of primary amines starting with an amide. Starting with an imide. Well, we really didn't start with the again. Yeah, actually we did. We started with an NH imide. So basically, this here becomes NH2R. By first putting on the R group and then hydrolyzing. Okay? It's a classical way to make a primary amine. But double hydrolysis, and you should be able to do mechanism here. Okay? Gabriel synthesis. Gabriel being the name of the chemist that developed this route to making primary amines. How else would you make a primary amine? All right. So you can show the product down there. And another reaction of amides is you can dehydrate a primary amide. If you dehydrate this, you'll actually make a nitrile. Okay? And it can be dehydrated with actually our old friend thionyl-chloride, which I think is the third time we've used thionyl-chloride. Okay? You should give this mechanism a try. If you have any questions, let me know. So that is a way to make a nitrile. Have you seen other ways to make nitrile compounds? What was another way?
Did we do it with our diazonium or something?
Do it.
When we did the diazonium reactions? Did
A
we get
diazonium, that would be a nitrile and an aromatic ring. What about on an alkyl carbon? What if you had that? Just do an SN2, replace the bromine with cyanide? Yeah. Well, this is another way. This comes from more of a carbonyl derivative, an acid derivative, an amide. Of course, this is going to be made from a carboxylic acid. So there's another route to get to a nitrile other than like an SN2. Okay, chemistry of nitriles will be next. Please be looking at that and be ready to ask questions about that portion there. Okay, guys, have a great day. See some of you in lab on Thursday. Tomorrow.